What's going on, class? Mr. Suffering here. Today, I would like to go over our notes for our lesson, thermodynamics. I know there was, I guess, some issues with regards to the notes and how the notes do not really line up with the slide deck. So I want to just take this time to make this video to maximize our time because we don't have a lot of time until our midterm. And I want to just go ahead and get this down and let it soak in. So let me just share my screen and let's get to it. Okay, so if you have in front of you your notes, it'll be really good for us to just go through this together and just jot these notes down as we cover each topic. Okay, so step one is define thermodynamics. So what is thermodynamics? Okay, and this slide, take a look at it. When you rub your hands 15 or more seconds, what happens? Well, your hand gets warm by way of thermal energy. Okay, thermodynamics is the study of the effect of work, heat, as well as energy on a system. Okay, so take a look at the caption on the bottom of slide 3, and it gives us, you have a system, and everything else is the surroundings. Okay, and a thermodynamic system examples would be a washing machine, air conditioner, or a refrigerator. If you take a look at it and think about an air conditioner for an example, an air conditioner is basically a closed loop system that circulates freon or refrigerant inside the system, which will alter the pressure of the refrigerant at different points to promote the transfer of heat. Okay, so think about a system and everything else is the surroundings, and there's and energy can flow into or out of this system in two ways, and these two ways are is through heat and through work. Okay, so if heat flows into this system right here, then the system gains energy. Okay, that energy is known as the internal energy of the system. The surroundings, however, can do work on the system, right? So these are the two ways of how a system gains its internal energy, by way of heat flowing into the system and the surroundings doing work on the system. So let's say, for an example, the surroundings performs let's say 100 joules of work on the system. Okay, that means the system's internal energy goes up by 100. All right, therefore, the change in this internal system is positive. Now, going to the first law of thermodynamics, I know I'm jumping around. Energy cannot be created nor destroyed. Energy can simply be transferred from one place to another. So if we have heat energy going into the system, well, that energy or heat is coming from somewhere. All right, since we're not God, we cannot create or destroy energy. Then that energy is coming from the surroundings. So if heat is going into the system, the system gains energy, and therefore the surroundings, the energy of the surrounding, it's decreasing by 100. Okay, so that's pretty much an analogy of a system. So if you if you take a look at the table on the top portion of your notes, it says list 3 examples of a thermodynamic system. Okay, so at this time, I would like to kind of just, draw a quick illustration. Okay, so let's say, let me share my screen and let me go to my document camera. Okay, so we have a system, and this system could be, let's say, a pot of water. okay? And this pot of water has a boundary, okay? So we'll say my boundary would be the pot itself, okay? Right? And this pot is basically separating the water from the surroundings. So that's what I'll put into that column right there, and with regard to boundary. Okay. And the environment, well, the system, let's say the system would be the water. Let's say this is water. Okay. So that'll be our system right here. And our surroundings would be the environment surrounding the system, which is the air. Okay. So if the system is going to, or the surroundings is going to perform work on the system, we would have heat. We just say that's fire. Okay. All right. So that is basically one example, one of three of the examples that I want you to give on your notes. Okay. So let me just stop sharing my screen and let's go back. Okay, let's move on. Okay, next, I want you to just go ahead and define thermal energy. I want you to go ahead and define thermal energy. Okay, I had to pause real quick. All right, so right now, let's go ahead and define thermal energy as well as temperature. And thermal energy is kinetic energy in transit from one object to another due to temperature difference. And that unit is joules, okay? Thermal energy, the unit of thermal energy is joules. And temperature is the average kinetic energy of particles in an object, not the total amount of kinetic energy particles. And temperature, the unit of temperature is degrees, okay? And we'll talk more about that as we move forward. Okay, if you take a look at our temperature scales, we have Celsius, Fahrenheit, and Kelvin. Celsius, the freezing point of Celsius is 0 degrees, and the boiling point of Celsius is 100 degrees Celsius. Fahrenheit, in which we here in the United States read our temperatures, the freezing point of Fahrenheit is 32 degrees Fahrenheit, as well as the boiling point is 202 degrees Fahrenheit. Then we have Kelvin. Kelvin, the freezing point of Kelvin is 273 Kelvin, and the boiling point is 373 Kelvin, okay? And we'll talk more about that as we move forward. Matter is made up of molecules in motion. So if there's an increase of temperature, then it will increase motion. Whereas if there is a decrease in temperature, motion decreases as well, okay? So just go ahead and jot that down on the bottom portion of your notes. Then there's this thing called absolute value. Absolute value is basically when all kinetic energy is removed from an object. And absolute zero happens when Kelvin reaches 0. And the conversion of that is negative 273 degrees. Okay, so go ahead and jot that down. Okay, here you will see, if you take a look at your formula sheet, and let me go to page 3, where you see our conversions. You'll see conversions on the bottom middle of page 3. You will see what you see on my screen right now. And these are the conversions of our 3 temperatures. Okay, so the only temperatures we're going to deal with is our temperature in Kelvin, which equals our temperature in Celsius plus 273. We have our temperature in Fahrenheit, which equals 9/5 or 1.8 times our temperature in Celsius plus 32. And then we have our temperature in Celsius, which is our temperature in Fahrenheit minus 32 over 1.8. Okay. The temperature in Rankine, we will not be dealing with any temperatures in Rankine. Okay. Now, when you are converting, our temperature in Kelvin to temperature in Fahrenheit and vice versa, notice that you see our temperature in Celsius is an avenue to complete our conversion. So we would need to convert, if we're going to convert our temperature in Kelvin to Fahrenheit, we would first need to convert Kelvin to our temperature in Celsius and then plug that number into our Fahrenheit equation. So let me just give you an example. Let me go back to my document camera. Okay, going back to my document camera. Let's say, for example, we're going to, let me use a pencil. We're going to convert 1 Kelvin to Fahrenheit. Okay. So first, let's just jot down our temperature in Kelvin formula, which is temperature in Kelvin equal our temperature in Celsius plus 273. Okay. All right. So from here, I am going to use our algebra to rearrange this formula to reflect what we're looking for. So we have what? 1 Kelvin, or 1, equals temperature in Celsius plus 273. And we're going to subtract 273 from both sides. Okay. And now what we have is our temperature in Celsius equals negative 272. Okay. So that is our conversion. So 1 Kelvin is negative 272 degrees Celsius. And let me just focus in on this screen right here. Let's see. There we go. Okay. So now that we have our temperature in Celsius, let's go ahead and just plug our temperature in Celsius into our temperature in Fahrenheit equation. So our temperature in Fahrenheit is temperature in Fahrenheit equals 9/5 or 1.8 times our temperature in Celsius plus 32. Okay. So we have 1.8, 272 plus 32. Take our calculator, because I am not going to do this in my head. 1.8 times 272, and we add 32, and our temperature in Fahrenheit equals negative 457.6 degrees Fahrenheit. Okay, so that is the conversion for Kelvin. So 1 Kelvin equals negative 457.6 degrees Fahrenheit. Okay, so that's how you would use your, convert one temperature to the next, okay? And let us go back to our presentation. Okay, so let's just move on. And again, this slide is basically what I just showed you. I modeled for you. It's basically taking your temperature in Kelvin, and it is basically converting it to our temperature in Celsius. And then they're in a roundabout way, they're converting using the temperature in Celsius, plugging into the Fahrenheit formula, and they're getting to the same result of negative 457.6 degrees Fahrenheit. Okay, so I believe if you turn to page, and again, these notes are not in order, but if you don't see thermodynamic equilibrium, just go ahead and jot this down. There it is. It's on the first page. Okay. So thermodynamic equilibrium is obtained when touching objects within a system reach the same temperature. So let's say if you put an ice cube in your hand, well, basically, when the temperature of the ice cube in your hand reaches the same temperature, it is said that those two systems reach thermodynamic equilibrium. Okay, so that's what that means. So when touching objects reaches in a system reaches the same temperature. Okay, and the zeroth law of thermodynamics states, if two systems are separately found to be in thermodynamic equilibrium with the third system, the first two systems are in thermal equilibrium with each other. Okay. So just jot that down, and we'll talk more about it when we're going through our practice problems. Okay, so if you can turn to your next page. Then it talks about thermal energy, heat transfer, and the most common types are as follows. You have convection, conduction, and radiation. All three of these types of energy, heat transfer, are irreversible. 100% efficiency is unattainable. Okay. Okay, so on your notes on the second page, it's going to, have you, list three types of heat transfer: conduction, convection, and radiation. And then it wants you to define these three heat energy transfer systems and give two examples. Okay, but let's go and talk about the first law of thermodynamics. The first law of thermodynamics states that energy cannot be created, nor it cannot be destroyed. It can only be transferred from one system to another. Okay, so that is the first law of thermodynamics. So an example, you have a pump, an air pump, that applies mechanical energy into a system that is converted into thermal energy when you are pressing down on the handle. So that is an example of the first law of thermodynamics. So, energy cannot be created or destroyed. It can only be transferred from one system to another. And just like this bike pump, it is just converting mechanical energy into thermal energy. And the second law of thermodynamics basically says that thermal energy flows from hot to cold. Okay, so for an example, if you put that ice cube in your hand, well, your hand is very warm. So your hand, the heat energy from your hand is being transferred from your hand to the ice cube. Whereas if you touch a hot slice of pizza, well, that thermal energy is going from the pizza to your hand. Okay, so that's what this slide is basically modeling. Okay. Then it's going, then this slide talks about entropy. And entropy is the measure of how evenly distributed heat is within a system. Okay, low entropy is a state of stability, order and balance. Okay, and high entropy is chaotic and disorderly. Okay, so that's pretty much what entropy is. Then it goes into convection and conduction and radiation. Just go ahead and complete the notes and give 2 examples of, convection, conduction, as well as radiation. Okay. So now we're getting into our practice problem. So if you can turn to our next page, okay, it talks about our conduction energy transfer equations. And all right, so let's go ahead and talk about it. So we have the following equation. So energy transfer equation, you have Q, capital Q, equals M times C times the change in T. And let's talk about what that is. So Q, capital Q, is the energy transfer in joules. Okay. So if you're looking for the energy transfer from, let's say that from your hand to that ice cube, okay, this is the equation you're going to use. Lowercase m is for the mass of the material in kilograms. Lowercase c is the specific heat capacity of the material, and the unit of that is joules per kilogram Celsius. And then you have delta T, which is the change in temperature. Okay. And then you have other energy transfer equations. You have your capital P, which is your rate of energy transfer in watts. Q, of course, is your energy transfer in joules. You have your change of lowercase t, which is time, and you must convert your time into seconds. Your lowercase t is your thermal conductivity. Capital A is your area of thermal conductivity. L, capital L, is your thickness of your material, and delta T, of course, is your change in temperature. Okay, so let's talk about these equations in a practice problem. Okay, so let's take a look at this. Let's calculate the energy. Here's the scenario. Calculate the energy transfer when a block of aluminum at 80 degrees Celsius is placed in a 1 liter or 1 kilogram of water at 25 degrees Celsius if the final temperature becomes 30 degrees Celsius. Okay, so I'm going to go through your slides and then go to my document camera and model how you would solve this problem. So your first step is take a look at your known values, list them, all right? Make your conversions and have all of your known values listed before you start solving, okay? So your mass of water equals M water, and you have that is 1 kilogram, and you have your specific capacity of water, and that is basically a constant. We already know that. They're going to give you that, which is 4,184 joules per kilogram Celsius. You have your change in temperature, which is 30 degrees Celsius minus 25 degrees Celsius, and our change in temperature is 5 degrees Celsius. And then you have your specific heat capacity for your aluminum, which is 900 joules per kilogram Celsius. And then you have your change of temperature, all right, for your aluminum, which is 50 degrees Celsius, okay? Okay. And your step 2 is list all known values. All right, so your known values, unknown values is what you need to solve for, which is your energy transferred and your mass of the aluminum block, okay? So basically they want to know, what is the energy transfer from the metal block to the water, okay? We want to know in joules what that energy transfer is, okay? And we also want to know, what is the mass of the aluminum that creates thermal equilibrium, okay? So these are the equations we're using. We're using our energy transfer equation. Capital Q equals mass times specific heat capacity multiplied by the change in temperature. And then now that you have all of your known values, you just want to substitute and solve, okay? So you have 1 kilogram, your specific heat capacity, you have your change in temperature, and you multiply that together, you have 21,000 joules gained, okay? So let me just take it to my document camera. Okay, so here's how your notes should look. Probably neater. Okay, so just go ahead and, whoops. Okay, so go ahead and list all of your known values. Okay, let's do this again. Let's go ahead and focus. There you go. All right, so go ahead and list all of your known values. So your mass of water is 1 kilogram. Okay, calculate the energy transfer from aluminum block. All right, so our aluminum block, the temperature of our aluminum is 80 degrees Celsius. Our specific heat capacity of our aluminum block is 900 joules per kilogram Celsius. Our specific heat capacity of water equals 4,184 joules per kilogram Celsius. Your temperature of your water is 25 degrees Celsius. Your temperature of water and aluminum at its final state is 30 degrees Celsius. Okay. Your change in temperature for water is 5 degrees. Your change in temperature for your aluminum is 50 degrees. Now, what is the energy transfer? Now that we have all of our known values and our unknown values listed, let's just substitute and solve. Okay, so we have 1 kilogram, which is our mass of water. So we're looking for our energy transfer of water. So it's 1 kilogram of water, specific heat capacity of water. You have your change of temperature for water, okay? So Celsius cancels out, kilogram cancels out. You have your heat capacity of 4,184 joules times 5, and you get a energy transfer for water, 20,920 joules gained. Okay, so basically what that's saying, since the metal block is warmer than the water, then the second law of thermodynamics, heat energy transferred from hot to cold. So the water is gaining energy. Okay, so that's what that says. Now we have, what is the mass of aluminum that creates equilibrium? Okay, we're going to use this same equation, but we're looking for mass. Okay, so just plug in the numbers that we have. So we have what? Our energy transfer is 20,920 joules. And we're looking for our mass in aluminum. And our specific heat capacity for our aluminum block is 900 joules kilogram Celsius. And our change of temperature for our aluminum block is 50 degrees Celsius. Now let's just go ahead and just solve, okay? So we have Celsius cancels out. And now we have 900 times 50, you have 45,000 joules per kilogram. And you just divide the two and you have your mass aluminum is 460 grams, okay? All right, so why do we have to convert kilograms to grams? I want us to have a discussion about that on our next class meeting, okay? So that's how you solve for your energy transfer from, two objects that are touching. So let's go ahead and go to our next slide. Okay. Okay, guys, on your notes, we've already completed our warm-up problem. Actually, here it is. We completed our warm-up problem right here. Okay. Now, if you turn to the next page, you're going to see a second warm-up problem. And it states a block of aluminum at 95 degrees Celsius is placed in a 2-liter kilogram of water at 10 degrees Celsius. The final temperature of the water in aluminum is 30 degrees Celsius. Find the energy transfer of aluminum into water. Find the mass of the aluminum. Okay, so we already did that in the previous problem. Now we have, what is the rate of energy transferred? What is the rate of energy transferred if it took 5 minutes to reach the new temperature? Okay, now taking a look at our equations right here. Okay, capital P is the rate of energy transfer in watts. Go ahead and jot all of this down. Okay, we already know what Q is. Let's just put Q right here. Q is our energy transfer in joules. We have a lowercase t, which is time in seconds. I'm going to actually put a delta right here because this is the change in time in seconds. Change in time in seconds. Our K, lowercase k, equals our thermal conductivity. Capital A is the area of thermal conductivity. Capital L is the thickness of our material. Okay. So take a look at these equations right here. Okay, take a look at these equations up here. We need to make one modification. Okay, so our thermal conductivity equals our rate of energy transfer times the thickness of material divided by, and this should say area times our change in temperature, so delta T. So go ahead and just make that quick change right there. Okay. So our rate of energy transfer, our equation right here is going to be our rate of energy transfer equals our energy transfer divided by our change in time in seconds. Okay, and that's how you're going to find out the energy transfer if it took 5 minutes to reach the new temperature. Okay. All right, this practice problem right here is calculating the energy transfer in a through an area of a wall. So let's take a look at it. Calculate the energy transfer in the wall section measuring 2 meters by 1 meter by 0.04 meter thick with a thermal conductivity of 0.1 joules per second meters Celsius. The opposing sides of the wall section have a temperature of 20 degrees Celsius and 5 degrees Celsius after 1 hour. Okay. So again, when you're thinking about, it's getting cooler outside and you want to make sure that you trap as much heat inside as possible so your power bill won't increase. So this is what we're thinking about with these equations, with these practice problems. Okay. So what are the equations we're going to use? Okay, so we're looking for the energy transfer. So we're calculating the energy transfer. So the first thing we're going to do, we're going to list our known values. Okay, so what's our known values? We have a wall section measuring 2 meters by 1 meter by 0.04 meters thick. Okay. So with that being said, this is our area. So if we're going to use let's just write down our equations first. So we have our rate of energy transfer equals our energy transfer divided by change in time in seconds. We also know that our rate of energy transfer also equals our thickness of material I'm sorry. So this is our thermal conductivity multiplied by the area of thermal conductivity multiplied by our change in temperature. All that is over our thickness in material. Okay. So again, we are looking for the energy transfer. Okay. So notice that our energy transfer, our previous equations was our Q, energy transfer equal mass times the specific heat capacity times the change in temperature. Well, this time we're going to use this equation in dealing with the area of a wall. Okay, so if I'm looking for our energy transfer, now we're going to rearrange this formula to kind of reflect of what we're looking for. So if I multiply delta, the change in time in seconds on both sides, I would have our energy transfer equals our rate of energy transfer multiplied by our change in time in seconds. Okay. Now, what is our rate of energy transfer? Well, our rate of energy transfer is this. Okay. So now let's just go ahead and rewrite our equation. So our energy transfer equals our rate of energy transfer, which is thermal conductivity multiplied by the area multiplied by, that's area, multiplied by the change in temperature. And that is all over the thickness of our material multiplied by our change in time in seconds. So this is our equation we're going to substitute and solve, okay? So let's now that we have our equation set up, let's go ahead and list all of our known values. So our known values is our area, okay? So our area, what is our area? It's 2 meters by 1 meter. And what does that equal? 2 meters squared. Okay, I'll just put a box over that. All right, so it's also giving us our thermal conductivity of 0.1 joules per second per meters Celsius. So let's go ahead and just jot down our thermal conductivity, which is 0.1 joules second meters degrees of Celsius. Just put a box around that. What else do we have? Oh, look at this. We have our, we have our thickness of material. I forgot about that. We have a thickness of material. And what is our thickness of material? 0.04 meters. And what else do we have? We have our change in temperature. What is our change in temperature? We have 20 degrees Celsius and 5. We're going to change this to 10. That's another typo, y'all. We're going to change that to 10. So our change in temperature equals 10 degrees Celsius minus 5 degrees Celsius equals 5 degrees Celsius. And lastly, we have our change in time in seconds. So now we want to know what the temperature is. We have a temperature of 10 degrees Celsius and it goes to 5 degrees Celsius after 1 hour. So we have change in time in seconds. So now, you know, we have to convert 1 hour into seconds. So going back to our conversions exercise that we did last week, our given unit is what? 1 hour. Let's just write the conversion right here. We have 1 hour. 1 hour over 1. And you have one hour equals what? 60 minutes. One minute equals 60 seconds. So we have minute that cancels, hours that cancels, and we have 60 and 60 equals 3,600 seconds. So our change in time in seconds is 3,600. There we go. Okay. Okay, now we just substitute and solve. Okay, so we have our energy transfer equals our thermal conductivity, which is 0.1. Joules, second, meters, Celsius, times, let's just put parentheses, times 2 meters squared times area times our change in temperature, which is 5 degrees Celsius. And we're going to put a parenthesis over all of this. And this is all over our thickness of material. What is our thickness of material? 0.04 meters. And we're going to put all the way over here our change in time in seconds, which is 3,600. Okay. Now let's just go ahead and solve. Celsius cancels out. What else cancels out? Seconds cancels out. What else cancels? So we have this cancels out. And let's just go ahead and solve. So we have we have 0.1 times 2 times 5 multiplied by 3,600. Now we have 3,600 joules, meters over 0.04 meters. And that equals what? 3600 divided by it, and meters cancel out. 3600 divided by 0.04. And our energy transfer is 90,000 joules. Okay. So that's how we would approach this problem. List all of your known values, make your conversions, simplify your equations, substitute and solve. Okay. Okay, guys, taking a look at the bottom of page 57 on your notes, you're going to see, and if you look at your slide deck on slide 24, you see U value. Okay, so your U value is a coefficient of heat conductivity. And this measures the material's ability to conduct heat. Okay, and your formula, if you can write that down, where you see define U value. Your U value equals what? Your heat conductivity, capital U, equals to the rate of energy transfer divided by your area of thermal conductivity multiplied by your change in temperature. And there are two systems of measurements we're going to take a look at. We're going to look at your metric system, and your U value in your metric system is watts per meter squared Celsius. And our US customary system of measurement is BTU over feet squared per hour per degrees in Fahrenheit. Okay, so that is, so jot that down where you see the define your U value, and then you're going to see your R value. Okay, so your R value is basically the measure of the material's ability to resist heat. The higher the R value, the higher the resistance. It's funny that we're talking about this because as it's getting cooler, I went into my attic and I saw the insulation of my attic is actually, you can actually see the floor joists. So with that being said, it's telling me that the R value in my attic is not sufficient to resist the heat loss in my home. So what I'm going to do is go to Lowe's or Home Depot, and I'm going to get this machine that actually you can put insulation in there, and it will, it will just basically suck that insulation from this machine, and it will just basically dispense insulation in my attic. Okay, so this is a really good segue to what one of my home projects is. So anyhow, so take a look at define R value. Your formula for R value is 1 over your 1 over U. And then you see your bulk R value, which is R value for one object plus the R value of another object. All that equals your total R value. Okay. So the objects we're talking about, it can be drywall, it can be the studs, the wooden 2x6 studs that's in your walls, it can be your brick veneer, etc. So we're going to take the R values of all of those objects, and then we're going to add them all together to get our total R value. And then we're going to use that value in a calculation. So let's take a look at it. Okay, guys. If you look at if you can look at your slide deck on page 26, on slide 26, as well as the second part of your notes that I amended, you will see on page 59, you will see a practice problem with the objects of your home. And with this, you're going to take a look at your R value chart, and you're going to get the total R value of each object that you are analyzing. Okay. So again, this says use the provided R value chart and the illustration below to calculate your bulk R value of the wall cavity and the R value at the stud location. Okay, so you will be able to see this in color on your slide deck, but this is actually your wall stud. And in between your stud, you're going to see in here, which is your fiberglass insulation, right? That's what basically traps, resists the heat leaving your home. Okay, so what we're going to do, let's just go ahead and just calculate the R value. So when I take a look at, let's start with the fiberglass insulation. I am going to go to fiberglass insulation, if I can find it. All right, here's our fiberglass insulation right here, and that is 3. R value is 3.142, and we're going to multiply that because we need 6 inches of that. And what do we have? We have 18.852. On your slide deck, they rounded to 19, so I'm just going to put 19. So your R value of your fiberglass is 19. Okay, so let's go to your 5/8 inch drywall, and we're going to say that is 0.56. We're going to say 0.56. We're going to say this is, well, we said R. Let me just erase this. We're going to say our R value for our drywall. Let's put it right here. Our R value for our drywall is 0.56. Insulation is R. R value is 19. And then what about our 2x6 stud? We have our 2x6 stud, and that is R value, R 6.88. Our foil face poly ISO is 720. Okay, and then we have our airspace. So our airspace on our R value chart, it says it's 0.95. On our slide deck, it says 0.17. I'm going to look into that, and I'm going to modify this R value chart. But let's say for grins right now, it is 0.17. So our airspace is an R value of 0.17. I'm going to just put a small line. We're going to put 0.17 there. Okay, and we have our brick veneer, our common brick. Let's find that on our sheet. All right, common, and that's 0.80. Okay, so now that we have all of the R value for our components for a wall, or objects for a wall, it says, wall cavity R value. All right, so what is our wall cavity R value? So let's list them all out. We have 0.56. We have 19. And our wall cavity, I want you to understand, our wall cavity is everything right here, for an exception of our stud. Okay, so we're going to say 0.56 plus 19 plus 720, 7.20 plus R17, so it's 0.17 plus 0.80 or 0.8. And our R value at our wall cavity is 27.7. All right, now what is our R value at the stud location? Okay, so now this is our stud location. So we take the R value of everything minus the fiberglass. So 6.88 plus 6.88 plus 0.56 plus 720 plus 0.8, and we get an R value at our stud location is 15.6. I think that's right. Let me see. 6.88 plus 0.56 plus 7.20 plus 0.8, 7.44, 15.44. Okay, we're good. All right. There we have it. Now that we have all of that, it's asking, what is the rate of transfer through the wall cavity if the area is 100 feet and the change in temperature is 40 degrees? Okay, so what equation are we going to use? Absolutely. We're going to use, let's just put it over here. We're going to use our U value equals our rate of energy transfer divided by our area of thermal conductivity multiplied by our change in temperature. Okay. Now, since we're looking for our rate of transfer, rate of energy transfer, we're solving for this variable right here. Okay, so if we multiply a delta T on both sides, we get, let's put it right here. Let's put it right here. We get P equals area times the change in temperature multiplied by your U value. Okay. All right, so since we are finding the rate of transfer at the wall cavity, we are incorporating our R value. So our equation for R value is R value equals 1 over U. And since we're solving for our U value in this equation, if I multiply U on both sides and divide R from both sides, we're going to have U equals 1 over R. All right. So these two equations, I'm basically going to be using. Okay. All right. So let's just substitute and solve. So our rate of energy transfer equals rate of energy transfer. Let me see. Equals 100 feet squared. Okay, so our rate of energy transfer is 100 feet squared multiplied by our U value. And our U value for our wall cavity is 27.7. So this is 1 over R. So we're going to say 1 over, where is it, 27.7? And the unit would be feet per hour, per degrees in Fahrenheit, over BTU. Okay, I'll put this in parentheses. And we have our change in temperature. What is our change in temperature? It's 40 degrees Fahrenheit. Okay. Okay. Feet square. What? Feet square cancels. Fahrenheit cancels. Now we have 100 by 27.7. I'm just going to write this out, 0.036 101083 BTU hour times 40. Now we just multiply that all together and we have times 40 times 100. And our rate of energy transfer is 144.4 BTU per hour. I'm left-handed, so I hope I wasn't covering my work, but there you have it. So to get to this answer, we're going to have to get our R value for all of our components, all of our objects within this wall. We have our R value at our wall cavity, 27.7. We have our R value at stud location, which is 15.6. This asks, what is the rate of energy transfer through the what? Wall cavity. Wall cavity. If the area is 100 feet squared and the change in temperature is 40 degrees Fahrenheit. So we already know that if it's Fahrenheit, we're using the US customary system of measurement. That is BTU over feet hour degrees in Fahrenheit. And then once we take the equations we're going to solve for, our U value, but we're looking for the rate of energy transfer within this equation. And we're also looking at this R value. So we're looking at, we need to solve for U with our R value. That's how we got that. And then once we have our equation set up, we just substitute and solve. Okay, guys, now that we've completed most of the practice problems, this problem right here on page 61 of your notes is more of the same, okay? And this was actually a part of our in-class project, but since we didn't have enough time, we're just going to just run through the practice problem, okay? So, and if we have time during the, down the line, we will take some of these projects that we did not complete in class, and we will, we'll do it. It's pretty fun. I think you will enjoy it. So let me share my screen and let us cover this last practice problem, okay? So you have a 1/8 inch thick acrylic testing box with the dimensions of 11 inch by 11 inch. It's covered with an unknown 3/4 inch material, insulation material. We are going to determine the thermal conductivity in watts per meter Celsius for the unknown insulating material if a 45-watt bulb is used to heat the box. The bulb maintains an inside temperature of 45 degrees Fahrenheit, higher than the outside temperature of 20 degrees Fahrenheit. Okay. All right. So the first thing we're going to do, we're going to list all of our known values, and we're going to make our conversions. Okay. So make your conversions. So list all your unknown or your known values. So 1/8 inch thick acrylic testing box with the dimensions of 11 inch by 11 inches covered with the unknown 3/4 inch insulation material. So we're going to start with our thickness of our material. Okay. So our material, we're going to call that L. Our thickness of our material is 0.75 inch. But we're going to have to convert this into what? Meters. So 75 inch over 1. And if we look at our formula sheet, let me find my formula sheet here. Here it is. Okay, going to our formula sheet on page 3. And we know that 1 inch equals 2.54 centimeters, okay? So I'm going to write my conversion. So we have 1 inch equals 2.54 centimeters. But we need to make our conversion to meters. So going back to our formula sheet, and we know 1 centimeter equals 0.01 meters. Okay. We're going to say 1 centimeter equals 0.01 meters. Now we can go ahead and solve. Centimeters cancel out, inches cancel out. So we have 0.75 times 2.54 times 0.01. And our thickness of material is 0.01905 what meters. Okay. So our area is 11 inch by 11 inch. Okay. So let's go ahead and write our known value. Area equals 11 inch. So we have to convert inches into what? Meters. So we have 11 inches. We already know 1 inch equals 2.54 centimeters. And we know 1 centimeter equals 0.01 meters. Inches cancel out, centimeters cancel out. So now we have 11 times 2.54 times 0.01. And we have 2.2794 meters. Since this is 11 by 11 inch area, we have 0.2794 meters times 0.2794 meters. And what do we have? We have 0.0780. Let's just write it all out. 0.6436 meters squared. Okay, so we have our thickness of material and we have our area in meters. Okay, now what else do we know? We need to determine the thermal conductivity for the unknown insulation material with a 45-watt bulb. All right, so that is our rate of energy transfer equals 45 watts. All right, so what else do we have? We have our change in temperature. What is our change in temperature? The bulb what maintains a 45-degree Fahrenheit higher than the outside temperature of 20 degrees Fahrenheit. Since it maintains, there is no change, okay? So the only thing we would need to do is convert Fahrenheit to Celsius. So our change in temperature equals 45 degrees Fahrenheit. And our conversion, what is temperature in Celsius, equals What's our equation for Celsius? Temperature in Fahrenheit. Fahrenheit minus 32 divided by 1.8. All right. So we're going to say this is 45 degrees. Our temperature in Fahrenheit is, let's erase this. Let's just say 45 degrees Fahrenheit. All right. And this equals our temperature in Celsius. So let's go ahead and just substitute and solve. 45 minus 32 divided by 1.8. Our temperature in Celsius is 7.22 degrees Celsius. Okay. Is there anything else we need? I think that's good. So we need one more thing. What equation are we going to use? Okay. What equation are we going to use? Okay, just to reference our formula sheet, if we go to page 3, we'll see our conversions, but continued, our conversions continued is on page 4, and you'll see thermodynamics, okay? You'll see thermodynamics, and the equation we're going to use is this guy right here. So we're looking for the thermal conductivity. Actually, as written on the slide deck, we have 2 equations, right? So our equation, our initial equation is our rate of energy transfer equals thermal conductivity times area of thermal conductivity times the change in temperature over the thickness of our material, okay? We'll put a line over this. All right, if you use your algebra to find what you are looking for, we're looking for the our thermal conductivity. All right, so that's what we're looking for. We're solving for K. And our slide deck did it, but if you used your algebra to rearrange your formula, you would basically get your thermal conductivity equals your rate of energy transfer multiplied by your thickness of material divided by your area of thermal conductivity multiplied by the change in temperature. Okay. Now, once we have this equation right here, we're solving for thermal conductivity. Now it's the easy part. We'll just substitute and solve. Okay. So, so we have our thermal conductivity equals our rate of energy transfer, which is 45 watts. 45 watts times the thickness of our material, which is 0.01905 meters. Okay. And that is divided by our area of thermal conductivity, which is 0.0780643 meters squared times our change in temperature in Celsius, which is 7.22 degrees Celsius. Okay, so now we'll just solve now. All right, so our meters cancel out. Okay, so now our thermal conductivity equals 45 times 0.01905, and we have 0.8775 watts over 0.07806436 times 7.22, and I get 0.56, 0.5636. Okay, and that is meters degrees Celsius. Now I'm going to take now I'm going to divide the two. Okay, thermal conductivity equals, let's say divided by 8775. Let's inverse that, and we have 150. No, something's wrong. Let me do that again. Let's say 45 times 0.01905. Okay, we have 8775. We have 0.078 times 7.22. That's better. Okay. 0.56316. Then we'll just divide that by 0.8775, and we'll inverse that. That looks better. 1.5, I'll say 1.56 watts per meter degrees Celsius. Okay. Okay, I know this is a lot, but the thing that you want to do, just really focus and just think about our rules. All right, so our first rule, you read this complex question and just break it down in chunks. Make sure you list your known values. All right, when you list your known values, make your conversions. Known values, make your conversion. Okay, and then determine your unknown values. Your unknown values, hey, we're determining the thermal conductivity. All right, find the equation you're looking for. Solve for, like rearrange your formula to reflect what you're looking for. Okay, then after you do that, substitute and solve, and you'll have your answer. Okay. The last thing we need to do, we'll just do in class. We're going to talk about the thermal energy transfer with regards to radiation in Stefan's law. That's pretty straightforward. It's more of the same. We'll cover that in class. But what I would like for you to do is study these notes, study the practice problems. I am going to embed this video in the Canvas, in our Canvas, in our homepage. You'll see it. You will also have the assignment where you can download and start completing. It's pretty much straightforward. I mean, just remember everything we've done in this video, reference the video and practice on it. And I think you'll be fine with this, okay? Tomorrow, we will not spend much time with this. We're going to go into centroids and beam deflection. So be ready. And then after that, we'll be studying for our midterm going over some practice questions, and I think you are going to be fine. So just study up, just look over this for a little bit. Don't put all your attention on it. And I believe you're going to be fine. Anyhow, if you have any questions, you know how to message me via Canvas, and I will see you tomorrow. God bless. Peace.